Chemistry 30 class. We're in equilibrium and we recently finished learning Ka, Kb, and percent ionization or dissociation. So here's a few problems that we have done and that we can walk through just to go over the concept. So the first one, we have some information given the concentration of the acid, and then we have the hydronium ion concentration, and we're asked to solve for Ka. So there is a simple formula you can use, and it is derived from ice. So if you ever forget it, you could set up an ice chart and figure it out, but it's good to memorize, and then you'll just always know it, and it will save you some time. So the formula is the Ka equals the hydronium ion concentration divided by your weak acid minus hydronium. Now, one thing we have talked about in class, because it's a weak acid, the hydronium ion is concentration is very, very small. So if we have it, use it. If you don't have it, you can ignore it in the denominator. So because we do have it, we're going to use it. So we would just put in our calculator 3.0 times 10 to the negative 5. We need to square that value, divide it by the concentration of your weak acid, and then we're going to subtract 3.0 times 10 to the negative 5. If you're doing this all in one step, just make sure to put some double brackets in the denominator. And when you're done, you should see the value 4.5, keeping 2 sig digs, times 10 to the negative 10. And then because it is a constant, or the equilibrium constant, you don't need to have any units because we don't have any. So this next one is about percent dissociation or ionization because it is an acid. If you're doing percent dissociation, it is talking about how much of the acid actually is forming hydronium. So in this case, our weak acid is only forming 1.3% of the hydronium, and we're asked to calculate the Ka. So what we want to do first is, if we know that percent formula is hydronium's ion concentration divided by the concentration of the weak acid times 100, we can plug all the values in. So 1.34% equals the concentration of hydronium divided by your weak acid, which is 0.10 times 100. So we can rearrange this formula to find hydronium, and when you do that and you plug it into your calculator, you'll get that the hydronium ion concentration is 0.00134. Now that we have that, and that's moles per liter, now that we have that, we can go and use that Ka formula one more time because that's what it's solving for. And if you just started by writing down the Ka formula, hopefully you would realize that we don't have hydronium, so we'd have to find it first. But we did have the weak acid. So we're going to fill it in one more time, just like with that previous example. So we'll replace hydronium into the top and in the bottom, and the concentration of the weak acid. So we'll have 0.00134. This would have to be squared, divided by 0.1 minus 0.00134. So again, putting that in your calculator, just make sure there's brackets in the denominator, and keeping 2 significant digits, we would have 1.8 times 10 to the negative 5, and that would be your Ka value. So combining 2 formulas to find Ka. This next one we have, it's a multiple choice question. It's again talking about percent dissociation. So we want to use that formula. Percent is the hydronium concentration over the weak acid times 100. So what we can solve in this case is for hydronium, which is great because if we have hydronium, we can solve for the pH. So let's go ahead and replace some values. So 10 will equal H3O positive divided by 0.40 times 100. So we want to isolate hydronium, and what we'll see is hydronium, the concentration will equal 0.04. And now that we have that, we can calculate the pH by taking the negative log of that hydronium concentration. So another formula we need to have memorized. Once we're done that, you'll see that value 1.397, and this value keeps going. Because it's pH, we still want to keep 2 sig digs. That 7 will bump that number 39 to 40. So you'll see here our answer is A. So that's with our Ka problems. But we can move on from here and start to look at Kb as well. So this one we have some information given us the pH of our 0.100 mole per liter sodium carbonate solution is measured to be 11.66. What is the Kb for the carbonate ion? So if you're looking at your Kb formula, it's similar. Again, it's also derived from ice, but instead of relating everything to hydronium, it is relating everything to hydroxide. So hydroxide squared divided by your weak base minus hydroxide's ions concentration in the denominator. So in this one, we want to recognize that sodium carbonate, right, that would dissociate into Na positive and the carbonate ion, so CO3 negative. And we have to notice that this part here is going to be a base, right? It's on page 8-9 of your data booklet, and it's the base side. So because we're dealing with a base, we need to be dealing with POH, not pH. So we're going to take this value and get the POH by subtracting it from 14, and you'll see that your POH is 2.34. If you have your POH, you can figure out the concentration of the hydroxide ion, because we can just do 10 to the negative 2.34. Now, when I'm doing this, I do like to work with that exponent, but if you don't want to work with the exponent, just turn it into that decimal and we'll still get to the same place at the end. So I'm going to divide by my concentration of my weak base minus the concentration of hydronium. I'm sorry, that's hydroxide. It's same thing as our previous formula for Ka. If we have hydroxide, use it. If you don't have it, you can ignore it in the denominator. So we have everything we need. We're going to plug this into our calculator, and you will see this larger number, very small number, 2.189. This number keeps going times 10 to the negative 4. And keeping two significant digits based on the two digits here of your pH, we will have 2.2 times 10 to the negative 4. Now, one more to take a look at, and that is what would the pH of a 0.18 mole per liter cyanide ion solution be? So in this one, again, we want to recognize that the cyanide ion, Cn negative, that is a base. So we need to deal with Kb, not Ka. So in this case, what we can do, because we do need a little bit more information, if we're finding the pH, what we can find from the one of our formulas is the POH. So to do that, taking a look at your Kb information from what we've seen before, all we have here is the information about the weak base. What we can figure out is that we also have information of Kb. It's just one more step, and that's the connection with that Kb equals your Kw divided by your Ka. So your Kw is on page 8-9 as well, so 1.0 times 10 to the negative 14. And you can use the Kb of the Cn ion, the Ka of the Cn ion, we just change it to Kb. So we take that value, again, this is on page 8-9 of your data booklet, and we divide, just making sure that you're keeping everything in brackets. So we do that and we get a fairly small number, 0.000016, and there's a few more digits there, but that's going to equal your Kb. So now that we know that, we can go to this formula. So let's do some replacing. So 0.000016, keep that value in your calculator. That's going to equal the hydroxide ion concentration squared divided by your weak base, which is 0.18, minus the hydroxide ion concentration. So here's an example where you can ignore it in the denominator because it is a very small value, and because we're solving for it and we don't have it, just don't include it. So now we're going to isolate the OH ion, so multiply that 0.18 to the other side, and then take the square root. So the concentration of the OH ion will equal 0.0017, that value keeps going, moles per liter. And then we should know, if you have the hydroxide ion concentration, you can find the POH by taking the negative log of the OH ions concentration, so plugging that on in. And you'll find that the POH equals 2.768, that number keeps going. And then if we want the pH, which is what we're originally asked for, you can do 14 minus that POH, and we get 11.23. Now just to notice, I am keeping 2 sig digs because when it's pH, the digits that are significant are after your decimal. As always, I hope you found this helpful. If you did, please subscribe. And if there's any other video I can do for you, just leave me a comment.